All right, guys, welcome to another episode of The Conscious Endeavor. We're here talking about physics, reality, life, all that good stuff. So I'm here with Zaki Ali today. We're going to be discussing, various things of music, physics, all sorts of things, waveforms, various things that apply to music. Zaki, you are a sound engineer, familiar with civil engineering, big on all those sorts of things. So in terms of wavelengths, music, all of those things, how they apply. I think it's natural for us to kind of understand how waveforms, naturally affect the physical world, in terms of color, frequency, vibration. We're very aware of those things, different colors or different frequencies. But in terms of music, right, we have waveforms and all sorts of things that apply there.
Yeah. It's interesting because I feel like music is often overlooked or not taken seriously in that world, whereas it's definitely something that should be looked at, or it's essentially the study of waves, and those waves can just it doesn't necessarily mean just sound waves. It can be, the study can really be applied to electromagnetic waves or gravitational waves, for example.
Especially converting those sounds too, because I mean, when we have music recording nowadays, it's all digitized, right? So like bringing that organic, sound frequency which travels through the air, through the waves, you have to digitize it and cancel it out. There's all sorts of things involved with that.
Yeah, I mean, digitizing it, it's interesting. 1995 is when everything went digital as far as recording. Mm-hmm. With Pro Tools coming out, and it's interesting to really look at the science. I mean, this is kind of off topic already, but you have analog versus digital, and what is the real difference there? It's more the fact that when you're recording digital, you have an interface that converts your audio to digital, binary information, zeros and ones, and people are always like, what's the difference between analog versus digital? That analog warmth, what does it mean? But it's really just, when you're recording this information as zeros and ones, there's different plugins that process that. And there's linear plugins versus nonlinear plugins. Right. And the linear plugins, like an EQ or reverb, when you go ahead and start stacking them on top of each other, and next thing you notice is the signal source that you have recorded is creating small phase issues within it and weakening the source signal. So the idea is really, as an engineer, to get the best of both worlds and use analog in the signal chain in order to retain the strength of the signal.
Right, 100%. Yeah, I mean, and to break that down a little bit too, I mean, if you're talking about binary, right, in terms of, it's being processed by a computer, you know what I mean? So you have these recorded sounds, which then, are essentially encoded in a binary format for a computer to understand, and then applying plugins or distortions, as most people are familiar with, of those sounds, it now modulates, I guess, also it in a binary way, which is really interesting. Also with music in general too, like we could talk about harmony and things like that, and there's a geometric relationship between how those waves move.
Definitely.
Right.
Yeah, I mean, kind of stepping away from the whole recording side of things and into music theory, music theory is something that's often overlooked even by audio engineers, ironically, whereas the engineering side is kind of focused on more technology nowadays. And, music theory side is it's like two worlds that have kind of separated in a sense, where it's become more of a niche thing that the guys that really understand the music are, musicians. Like, that's all they are, really. But the understanding of waves, right? So, like, in ear training, or say like ear training, it's a course you would take in music school. You'll talk about intervals, the distance from one note to the next, and the qualities of those intervals, whether it's consonant or dissonant or perfect. And sound is really the only form of wave that I think people have gone into like training the brain to really understand and like hear those differences right away, and taught as a, you know, as a subject in schools and stuff. So
Right. Yeah, I mean, music in general too, when you're writing, it's really this process of like going between consonance and dissonance, right? And I think the average ear, like the average human ear, can really pick up on those things somewhat inherently. Like you can identify dissonance, right, as something that creates kind of a tension almost in the sound, and then a lot of times they'll create that tension and then they'll have resolution in the music. And there's really like an interplay, especially when you're like writing music, you know, diving
Definitely.
between consonance and dissonance and playing with that. And, you know, there's an emotionality to all of that as well.
Definitely. And I think, you know, while we're talking about music, and we're talking about pitch specifically, so like, you know, music or everything we hear, we're hearing the pitch, you know, what note we're hearing, whatever object is resonating at. And then we have rhythm, you know, so like keeping a beat.
Yeah.
And then there's dynamics, how quiet and how loud something can be. So every sound we're ever perceiving is going to be, the human brain perceives it in those terms. And then us defining it, I mean, you know, there's like a concrete study on how we'll go about defining that, and rules that were essentially that we're following that were created by like Mozart, Beethoven, and classical music. And I don't think like most people truly appreciate the genius of that until they get into studying some music, and it's
Right.
like, wow, these guys really were geniuses, you know?
Yeah, there's like counterpoint and things like that they're doing.
Yeah. Music counterpoint, study of harmony. It'll talk about how on certain beats you should have certain intervals in order to be musically correct.
Rhythmic beats.
No, well, rhythmic and pitch. So like, yeah, rhythmic beats. So like, say on beat on the end, or like one and two and, if you're counting eighth notes, like the one should always start on the tonic or the root note or the fifth, if which is still considered correct. And then, you know, on the ends you're able to have dissonance, but after like beat 4, it's like more correct as opposed to not. So there's like, it's just like a guide map for like what's musically correct.
Right.
But again, like it all comes down to like how the human brain perceives it. Like, you know, why is it that when we hear a major scale, people refer to it as happiness versus a minor scale where people hear it as sad?
Right.
And it completely changes the mood and affects how you visualize like a movie or anything, really. But
right. Yeah, there's a lot going on. I mean, especially emotionality of these like tonal structures, right? Which are just really like spaces that are in between these notes, like a certain amount of interval, right? So like, I mean, and again, to break that down a little bit, it's like, you know, you might have the root note, right? Which we start on, which could be, I don't know, let's just say 440, right? The octave of that being 880, right? Exactly, mathematically double of that frequency. And we all know that from like somewhere over the rainbow, you know? So it's like you have this perfect relationship, which is all based in mathematics, you know what I mean? And then understanding that, I mean, implicitly when the brain hears that, there are certain, as you said, intervals or certain relationships between those notes that naturally the brain just enjoys, like that there's a preference there, which is really interesting to think about the physics of like, why does this specific relationship between frequencies get interpreted by the brain as like pleasant, right? And other ones don't, you know what I mean?
I mean, it's interesting because like, you know, the way, you know, talking more about psychology and the way brain perceives sound, you know, essentially your brain is like creating pattern recognition, you know? Like, and the fact that we can go so deep into pattern recognition with music, and being able to identify pitches and rhythms, and I mean quiet, loudness, amplitude of a wave, it's quite fascinating to the extent of which that goes. But you know, also related but not related, you know, on the physics side, there's different theories that led us to believe, you know, not believe, but are that brings us to our modern understanding of what physics is today, right? So, you're starting with people like Isaac Newton, and an object in motion will stay in motion unless acted upon by an outside force and stuff. And then fast forward, you have Galileo with the telescopes coming out and stuff. And, you go to Einstein, and the theory of relativity basically talks about how space and time is one thing, right? So there's this relationship now where I feel like physicists are not so, I guess, like well versed in the study of time itself, but will rather look at space. So it's like, how can you relate those two things in order to further what we know about physics? So like the big question now in physics is really, there's relativity, which is the defined set version of what everything is, versus quantum, which is basically giving yourself a set number of choices. And it could be any one of the given, like a multiple choice answer.
Right. And you're saying in terms of quantum fluctuations, those are essentially probabilities moving in space. I mean, everything in essence has a vibrational quality to it, right? And that vibrational quality, I essentially can, as they say maybe in string theory, for example, which is like the deeper layers of atoms, that the nature of the vibration of those strings brings about kind of how the matter resonates, or how the matter, forms itself. So it's interesting to think even that music, in a way, being this idea that, we have a relationship of pitches, we have relationships of vibrations that, again, inherently change the human mind, and also have a relationship in themselves in the mathematics. It's kind of a really kind of divine interplay between our perception of, time and space, even because, vibrations and sound moving through space, and it's something, again, in rhythm occurs in time, right? And again, as you said, this pattern recognition that's inherently going on, what I mean? We can break that down, even further, but it's very interesting.
Definitely, like, I guess when it comes to quantum, the best example is like the double slit experiment.
Right.
When you have the light shining on the two slits and like the perfect amount, but like from the perfect distance. But then on the other end of the slit, you see 5 different patterns. And the way they describe it is, light, like, what is it? Is it a wave, or is it,
A particle, yeah.
Right, a particle. And I guess essentially the decision is that it's both at the same time. But yeah, exactly. Like when you shine the light through this double slit, you basically have 5 different beams of light showing up on the other end.
Right, which is the interference pattern, right?
Right.
So yeah, the double slit experiment being the fact that they're shooting electrons through a device, and there's 2 slits or 2 holes in which the electron can move through. Yeah. Now, when they shine that light just naturally, the light can go through both of these slits. They will then, as move through waves, they'll interfere with each other at certain parts, and the waves also combine at certain parts. Yeah. So then we get this interference pattern, which means that those particles inherently are moving as waves. But when we put observing devices there, right, they actually just move linearly. Yeah. Right. So it's interesting how this is where we get into the idea that the expectation of what we're observing and how we observe it changes the ways that these, subatomic things behave.
And, like, it all really comes back to Einstein and like the way we think of physics and what the implications of the theory of relativity really are when talking about this stuff. Because, just like, we could talk about light waves, but there's so many different aspects within the theory of relativity that can apply to our modern understanding and study of physics. You talk about space-time as one thing, like the implication of just that. Like if we look out into the sky and you see these stars and we're like, wow, this is so beautiful. What are we looking at right now? And then you take into consideration that everything you're looking at is millions of years ago.
Right.
It's not even
because of the
it
time,
already happened.
Right, because of the time that it takes the light to reach
Right,
us.
right. And
Right.
you know, like to put it into perspective, the closest star to us is 4.5 light years away. So the closest star, if you could spot it amongst the billions of stars out there, is 4 years away from us. And you know, to take that into consideration, like, you know, people talk about the Fermi paradox, or why haven't we seen life anywhere? And maybe, you know, that's a huge part of it. We're just looking back in time so far that nothing's happened yet.
Yeah, that's the crazy thing too with these telescopes. I mean, we look into very, very deep areas of space, and again, the farther away you look, technically you're seeing things farther away in time, right? So it really does become this really weird paradox where we have, you know, we're actually looking into the past, astrophysics, like speaking, you know, astrologically speaking. We're looking into areas of time. And also it's interesting too, because it leads us into understanding the formations of galaxies, how they may have formed and things like that. But, you know, these waves are propagating across space, and they get stretched and they get pulled. And in terms of gravitation, right, they're always moving, and they're naturally being distorted and bent and, you know, moved around.
So, I mean, here's the thing. Like, relativity, it works beautifully from our perspective and our size in the universe. But now, when we talk about the smallest of small, or like on a molecular level, things kind of become more quantum.
Right, and chaotic.
And relativity kind of falls apart. And the same happens when you talk about, you know, the size of the galaxy. Things in relativity don't necessarily make sense. And so that's like really like where are we bridging the gap between quantum and relativity to have the unified universal theory? And that's like the big thing that everyone's after.
So. Yeah, the interesting thing too is that like merging those, I mean, what I like to think about it as like there's two different domains of physics, right? Or there's domains in which certain laws apply. You know, we talked on a previous episode with my other friend Joe. We talked about how, you know, Brownian motion, for example, was one of these things where particles are actually chaotic and they're hard to predict where one individual particle may go. But when you pull back and you look at this motion, let's say of molecules, right? They're actually very predictable in terms of their macroscopic motion, right? Where you can see that laws like thermodynamics and all these other laws apply, and we can tell generally what's going to happen to that gaseous state of molecules. But if we're to zoom in on one, it's completely unpredictable.
You won't see it,
You know what I mean? And it's you don't know where it's going to go. You don't know how it's going to behave. It can bounce off various things. There's all sorts of, I think, you know, things like electrodynamics play a huge role in the movement of matter and particles. But, you know, when we get to those larger scales, when we talk about gravity, it's just like the absolute mass of material now applies to a different law.
Right.
You know?
I mean, it's also important to consider the fundamental forces. You know, the electromagnetic weak force, strong force. Gravitational force is the weakest force by far. I mean, so much so to the extent where it takes the mass of a planet to hold us down at negative 9.81 meters per second. You know, so it's really interesting to consider, or like to even think that like we have some sort of calculation that, okay, this is what gravity is. But then again, when we talk about greater proportions, I mean, larger than solar systems, we're talking about galaxy super clusters and stuff. That whole model of gravity kind of falls apart. You know, so
it's interesting to take into account too the fact that everything spins. And I think that there's a lot of embedded energy in terms of galaxies, planets, and stars, because all of them are spinning, which to some extent, as things collapse within each other due to gravity, they naturally tend to spin.
Not everything spins, but you know, it's kind of the same. Going back to Newton, an object in motion will stay in motion unless acted upon by our outside force. There's so much chaos and stuff happening out there between planets and whatever that gravity does knock things into orbits, and there's things like the moon is like tidally locked to us.
Right.
So
Right.
it's actually not orbiting, but it is gravitationally like spinning around us.
Stuck.
But,
Yeah.
yeah.
And it's interesting too, like where it comes in from. It's like a point of reference whether something's spinning or not.
Yeah.
Right. So we talk relative space versus like absolute space. It's like it
Yeah.
looks to you that it's spinning, but in absolute space, like, is it spinning? But I mean, the Earth, the sun also, I believe, orbits around a larger star, which has this whole implication in the grander scheme of the galaxy, which spins, which is spiral in nature.
Right.
The supermassive black holes are spinning like ridiculously fast, which are allegedly at the center of these, galaxies. But
yeah, I mean, when you talk about things but so much mass, like gravitational, like a black hole or a neutron star or something. A good example is to think of it like a ballerina, like when they're spinning, and then as they bring their arms in closer together, they start spinning faster, right?
Right.
Which is exactly the same thing, except like you have so much matter just compressing at one time, and it just increases the, the momentum of it.
Right. Yeah, it's interesting too. I mean, just to bring this kind of together too, there was the theory, I think it might be in ancient Greek, you may correct me here, but it was the music of the spheres, that this idea that there was sound emitted from every planet, and that there was, again, similar to how music has these geometric relationships.
Resonant frequency, basically.
Right, between, specific notes. Also that planets would form in similar geometric relationships.
Right. So I think that was really like the start of, kind of this big question of, in a way, how are we bridging the gap between relativity and quantum physics?
Yeah.
Which is also like a huge statement to make. But I mean that in a sense where, if you look at what our study of gravity is, like gravitational waves, were only proven 3-4 years ago, tops,
Right.
Like, meanwhile, the theory was from the 1920s, and the way in which it was proven. So we have sound waves, we have electromagnetic waves, and these intervals and distance between things correlate, So gravitational waves, the implications of that is essentially, you talk about sound waves, you're talking about waves moving through our atmosphere, within our atmosphere. Things will resonate a certain way because of the amount of pressure, air pressure, and, they'll have different qualities. But when you're talking about space and time itself as a medium, the waves within that kind of take out the factor of friction, is essentially like, people say music is a universal language, but you can quite literally think of it as that. And now, how is it that we prove that gravitational waves exist? We have, like LIGO. I don't know if you've heard of this. Like
yeah, a little bit.
Laser Interferometer Gravitational Observatory. So there's 2 in North America, and there's one more, I believe, in Italy.
Yeah, and just to break it down too, lasers that are used, right? They have essentially a laser is like a beam of light that's I guess you could say particleized, but it's linear light, which we can observe. It should be constant, right? So if it's not constant, they're inferring that something of the medium of space is altering the consistency of those.
Right. The lasers itself stay constant. So the thing is, it's essentially one laser that's shot in one direction in a tube that's 4 kilometers long, 4 kilometers in each direction.
Wow.
And so the way it works is they have a mirror at a 45-degree angle at the corner, and they have a laser that shoots off a mirror, bounces back, shoots off of this mirror, and bounces back 90 degrees, 4 kilometers the other way, right?
Wow.
So the idea is that on the mirrors at the ends, you can detect the slightest amount of movement, right? And so you have to think, like, what if an earthquake happens? Obviously, it's going to interfere with that,
right?
More so than like gravitational wave. But
right.
The way this was really proven is, you have three of these observatories, and when you get a reading in all three at the same time, you can kind of triangulate where the signal is stronger as opposed to weaker. So there were some readings, I believe the first in 2017, 2018, where there was a signal picked up by all three, and we looked and we didn't see anything. So the prediction at the time was that it was a black hole merger.
Right, the two black holes are orbiting each other,
coming together, and eventually just merge. But
ripping the fabric of space.
Right, something that's creating so much dissonance in space and time that it's being picked up and felt essentially here on Earth. But it's so minute and so many millions of years away that we don't feel it.
Right.
But it is happening, and but it still wasn't proven at that point, right? So we had gotten this signal, and then in 2019 it essentially got to there was multiple signals that were picked up in between, and in 2019 it happened again. There was another signal, and all these telescopes pointed to where the strongest signal was coming from. They had a general idea of where in the sky this was, and they look, and it was a neutron star merger.
Wow. So
they got the reading, they pointed their telescopes, they look, and they actually see what's happening now. And now they can prove okay, gravitational waves are a real thing. So now going back to ear training and the study of waves and how they correlate with each other,
right,
this essentially means that those properties also apply to gravitational waves. So, how can you use that understanding of pitch and time and relate it to the universe, really?
Yeah, I mean, it's interesting, too, because you have various levels, I guess, of distortion, right, that are occurring. Like if you have a particular medium and then you distort that medium, anything that you push through that medium is inherently also going to change. It's kind of like putting a phaser or a distortion on a clean guitar tone. It's like there's going to be modulations that happen. And it's interesting, too, how we even study these modulations or changes of frequency, right? Like they talk about how we know that the galaxy is expanding. For instance, they have the Doppler effect. And we're all really familiar with the Doppler effect because when a car is going towards you, right, the pitch is lower. And then as it goes away from you, actually it's the reverse, right? Pitch is higher because it's being compressed. And as it moves away from you, the sound source is moving away, it gets stretched. So we have that kind of so that sound wave distortion as an object is moving applies to literally every waveform, every wavelength, and it applies to light as well. So
you have redshifted
so
light waves, basically. The things that are really far away, we only see the infrared spectrum of it because the wavelengths have stretched so far over so much time.
Right. And that's interesting too, because again, the stretching of those wavelengths, there's a certain amount that it changes. And it's a really small vibration, or because also another crazy thing is that we can look at how that we can tell the composition of a star based on its color. Yeah. Right. So when we do that, we're able to, certain molecules have a certain, color to them, and how in terms of how they burn in stars. And those are very, distinct platforms, and you can tell what's burning in it depending on the color, but then also those colors will be there, and then we could say, okay, this is nitrogen, whatever that's in the star. But then if they're slightly shifted, we can tell the direction in which that galaxy is moving based on those small fluctuations. So there's all sorts of implications of waves and things like this just on the visual spectrum, but it's also on the auditory spectrum, which is just wild.
Yeah, I mean, the auditory spectrum, looking at it in terms of different waves, sound waves, electromagnetic waves, gravitational waves, whatever it is, magnetic waves, yes, the idea of music theory, the study of music theory could be applied to all, but what are the effects and how... it's kind of like thinking of the relationships between the different mediums. But there's definitely answers within that, I mean, we were just touching on different light waves for stars. or different characteristics of the stars to show you like the temperature of a star, the size of a star. Super. I don't even remember the term exactly, but you have different
Its compositions.
red giants, and like our sun doesn't necessarily burn so hot, or it's not like such a huge star. But then you have like really hot stars, which will be almost like a bluish color, and burning like hundreds of thousands of degrees, millions of degrees hotter than our sun and stuff. So,
yeah, it's interesting too, because we talk about music, and there's the difference with music and how there's, we have a resonating body essentially. So depending on how that, let's say the length of the string, or the size of, if we're talking about like a brass instrument, the size of the, tuba or whatever, compared to those, because of what their size is, and also what their material is, like waves will bounce off of those things differently, giving them different qualities, embedding different, really, which is interesting too, is embeds different information in the sound wave itself. And then the listener can hear like, oh, that's a saxophone, that's a trumpet, and you can tell by these, which are really embedded, in the waveform, which is interesting.
It's not even so much in the waveform, but it's within matter itself. So like, everything. So Tesla, like Nikola Tesla, not Elon Musk Tesla.
Gotta make that distinction now.
Had stated that every object has a resonant frequency, where if you were to have an oscillating frictionless motion at a specific frequency, you can completely destroy any object in the universe. So there's a certain frequency that if you have an oscillating, let's say like a piston, a frictionless piston that moved at a certain frequency with a certain amount of amplitude, that you can essentially just destroy the earth. Just like that. And any piece of matter, really. So
I think a good analogy to take there too is like the fact of like adding energy to a swing, right? And if you keep pushing at the right point, you can eventually, like, let's say, make that person like go all the way over, right? If you keep adding energy to the system in an appropriate and synchronisant way, right?
Yeah, I mean, that's an interesting way of looking at it. I guess it's really like, how these waves are like correlating and everything works together, and from a physics standpoint, on like a very grand scale, so going back to what I was talking about, how relativity is our modern understanding of physics and everything we study, but it completely falls apart at like the grander scales. Like you're talking about galaxies. Why does it fall apart? Because according to the calculations of our, supermassive black hole, Sagittarius A star, whatever, at the center of our galaxy, a mass of like 13 billion suns or something, we're close to around 13 billion suns. According to the theory of relativity, if an object with that much mass was in the center of our galaxy, then it doesn't make sense that our galaxy is staying together and orbiting around it. There isn't enough gravity, because there's so much matter in our galaxy that, according to the theory of relativity, everything should be just
flying off.
Like centripetal force. Just so it's interesting seeing, taking note of the fact that there is on that scale some other force that we don't know about, that scientists refer to as dark energy, dark matter, which is also just like a made-up thing. It's not necessarily like proven yet.
It's the missing proportion that needs to be there in order for the math to work.
Like, how is the theory of relativity changing from like in an exponential factor as it gets to that proportion? What is it about the theory of relativity that is holding all these stars together?
It's interesting too, like, you have the idea that all of these things again are creating, there's a book written called The Electric Sun, and there's a someone out there as a physicist, and he's trying to, push this theory that the sun is actually much more like electrical in nature than it is gravitational in nature. And maybe that, I'm not too sure if that kind of solves some of these issues, but also like fundamentally how we understand what these structures are doing in terms of stars, like how, because we know that for a fact that when, an electron moves, the movement of electrons allegedly is electricity, right? And electricity naturally is it's electromagnetic. So when that electron moves, it induces a magnetic field. So it affects the medium of space around it.
Definitely.
So when you have all of these particles of matter that are interacting, what is the magnetic counterpart to that? Is there a larger magnetic field? Or because again, magnetism is invisible.
On like a planetary level, the magnetic poles, north-south poles, it's all determined based on the core of the planet on the inside. The material of the core of the planet, like all the densest materials end up in the center. In our case, like iron and, the heavy elements. So like by coming together and spinning at a certain speed, you're essentially creating like a huge magnet.
Right. A dynamo, I think they call it, right?
Right. So, that's really the idea behind it. But what's really interesting, recently, it's years at this point, but the Voyager 1 spacecraft, launched in the 1970s, has just made it past the edge of our solar system. After 40 plus years of traveling, it finally gets to the point where it's beyond our solar system. And as it's getting to the edge, there was an edge of the solar system. Let me look up the term for this exactly.
The event horizon? Or
no. That's the edge, beginning of a black hole.
I know that they have like the Oort cloud.
Cloud, that's what it is. So the Oort cloud, right, is essentially the magnetic field of the solar system.
Right, wow.
Right, so like you're getting through this point, and then you're finally considered to be what is deep space.
Right.
So yes, the magnetism definitely plays a factor on the larger scale as well, in terms of the solar system. But as far as galaxies are concerned, we are just way too small, infinitesimally small to like even comprehend, like what is actually going on out there.
Right. Yeah.
But there is a unified theory that will bring it all together.
It'd be interesting if we hit the edge of the Oort cloud and because also like magnetism naturally obviously repels and moves objects.
Yeah.
So it's an interesting thing that we're hurling a hunk of metal at like a ridiculous speed to see whether, it's interesting to think whether or not it's going to be affected by this magnetic field, or also maybe how transmission of the signal back and forth maybe would be if we go beyond that Oort cloud. Right, beyond that magnetic field, whether or not signals can go through that.
Right.
These are like just totally untouched territory in terms of.
Another big thing, we're talking about magnetism, is how magnetism and magnetic properties are affected based on temperature. In space, it's not, friendly environments for humans at all. But
no air to breathe out there.
Well, yeah, no air to breathe. But the temperature itself, right? So, like, what happens in like an MRI machine? It's essentially like a huge magnet,
right?
But it's filled with liquid nitrogen in order to have certain magnetic properties to be able to visualize, scan the different parts of your bones and stuff. So, supercooling, the properties of superconductivity as the temperature is brought to sub-zero temperatures is definitely something to consider. And like it dives into a realm of kind of unexplored territory as well. So I think that can in a way even play into the theory of how gravity acts upon like giant objects, especially on like a grander scale like that.
Yeah. On the planetary scale too, it's interesting to think when we have a sun, right? And the sun is essentially the initiator of all molecular motion, right? It's heating up the oceans, which creates, differences as the Earth, rotates. It's creating tides. It's creating all sorts of things. And plants, again, chlorophyll and all these things like are catalyzed by photons, by the energy that's given by the sun. So to think about, when you get so far away from your host star, right? Like, what's going to happen to the matter that's there? You know what I mean? Like, in terms of there's literally like almost no energy hitting you, being added to the system. And we know with thermodynamics that things naturally will decay and equalize to their environment. If you're in deep space, whatever the hell that means, right? Like, there's no, like, the metals that these satellites operate by, like, how are they gonna act, how are they gonna react? And like, over time, being in an inhospitable environment like that, the electronics on these systems, you know what I mean? It's like kind of like trying to send a signal, like through, I guess, literally empty space, but it's like, what happens to these? How do they decay? And does the machinery, like, where is it getting its source from? I guess it has solar panels or something on it, but
I mean, there's different forms of, space travel right now is obviously like at a very, very beginner level, so to speak. Like, it was like I was saying, the closest star, like, it's 4.5 light years away. If we were traveling the speed of light, 186,000 miles per second.
Ridiculous.
It would take us 4.5 years to get to the closest star.
And we can't even get to like 25%.
Right. Even getting to
and those are like molecules. We get to those speeds, like not talking satellites.
We can get molecules on them, like with CERN and Large Hadron Collider. We can get those particles up to 99% of the speed.
Oh, really?
Yeah, it is. So that's why there's so many questions. Right. We're exploring realms that have never really been touched by humanity.
And the interesting thing is those things are being sped up by magnets.
Right. Yeah.
Right. You just put the
super magnets.
Yeah, and it just goes and goes and goes, and you keep, again, I love the analogy of just adding energy to the swing. You know what I mean? Like, you just keep adding energy to that system in an appropriate manner, and you can just accelerate. And that's, I mean, even with like they have plasma generators now, where they're able to kind of create plasma, which is electrons in almost a liquid-like state, but they're controlled by magnets. And they essentially, plasma being the fourth state of matter, they can kind of, I think it's a vacuum that they have, and then they put the electrons in this vacuum, they accelerate them with the magnets, and they get this kind of gelatinous massive electrons, which is what plasma is. And plasma is what lightning is, essentially.
So it was really interesting. I mean, okay, two subjects to touch up on, but more recently, I would say within the past 2 years, there was a observation of stars revolving closely around our galaxy's central black hole, the supermassive black hole. And there was a characteristic of those stars that was studied where, as the ones that would get really close, rather than keeping its shape or completely shredding apart, the star would almost turn into like a teardrop sort of shape.
Yeah, because it was being pulled.
Which was almost like the form of plasma that you're talking about. Right. In a way, but it's probably because, like, I can't even imagine the super, the temperatures that thing, the stars are facing over there, and the gravitational forces, and then all the different effects.
Enough energy to like rip it out, and It's interesting to think, is that actually physically happening? Because what we are observing, I mean, are we just observing the distortion of the light? I mean, maybe
no, it is physically happening.
Yeah.
So, like, we can't physically see that far.
Right.
But we have to look at it in radio spectrum. So, in order to see through all the dust. Right. But then we can physically see the stars. And then see them whip around an object that we can't see at millions of miles per hour. So something is there. It's it's the black hole, which we've essentially taken a picture of at this point.
And radio waves are really slow, right? They're much, much slower than most wavelengths. I mean, they're way below.
Infrared is the longest wavelength, right? So like the longer the wavelength, the further it'll travel.
And then I believe radio waves are below infrared.
I think so, yeah.
Yeah, because then we have on the opposite spectrum, like X-ray, gamma is like way up here. Then comes the visible spectrum being in the middle, infrared, And then we have like radio.
That's
and
another
all-
like really interesting thing to touch up on is how small the visible spectrum really is. There's this really funny analogy where if the entire electromagnetic spectrum was the size of the state of California,
Okay.
from top to bottom,
Right.
that the visible spectrum, everything we see, is about the size of a penny within that. Oof. Which is like so crazy to think about.
Yeah, because imagine, I mean, in order to even zoom out to see the length of, the state of California, like you got to be in space. Like you have to see, just to see that. And then imagine trying to see a penny.
Yeah.
Even from like 100 feet up, trying to see a penny is probably difficult. You know what I mean? Like now pulling all the way back, it's infinitesimal. Like you can't even, perceive that. It's just wild. But
I mean it's great because like the telescopes we have nowadays are powerful to that extent. What is it? The James Webb telescope that just came out. They say, well, obviously it's the most powerful telescope, but they say that looking at the central black hole, like in our galaxy, it's so far away, it would be the same as if you're zooming into a penny on the moon. So I mean, it's just talking about pennies here, but
yeah, I mean it's interesting too, just the refraction of light and how we're doing that with just different layers of bent glass essentially, and refracting and moving, and it's just absolutely wild. But I mean, going back to this idea of the visible spectrum being so small, it's like interesting how organisms on this planet allegedly, we picked a very specific and varying degree. I mean, the degree between red and blue are very different, and we make that distinction. I mean, in terms of if we're looking at the full electromagnetic spectrum, they're ridiculously close to each other, but our apparatuses or like our sensory, organs have developed such acuity to distinguish differences, let's say in the color of one flower versus another, or one berry versus another, which for us, there's like a huge survival instinct built into our ability to discriminate certain colors and certain, frequencies and what that, tells us. I mean, even being able to identify a prey animal or a predator, or like differentiate them from the environment. Yeah. It's interesting how we are able to pinpoint those little things.
Yeah, definitely. I mean, there's so many unanswered questions in physics at this point. Like we have a good general idea of like the way things work, again, like at our proportion. And it is fascinating how minimal the differences can be, that our brains are able to perceive and pick up on. But at the same time, like we're also so insignificant compared to the grand scheme, like the picture, to the point where like when we get to that level, it doesn't even make sense.
Yeah, I mean, interesting too. A quote that I love. I mean, we are a product of physics in a way. I mean, life, arose out of it. And there's interesting too, because you can take the idea that they're kind of the antithesis of each other, because thermodynamic decay is always happening, and all these things in life, in a way, is kind of fighting against these forces. Like we're always giving off heat, right? But which is losing energy. But then we consume things to maintain that energy, and we burn things within ourselves to, I mean? So it's really interesting how biology inherently as a function, as a mechanism, has kind of observed, let's say, these laws, and then found ways to maintain function regardless of, the decay of, I guess, the natural world, or the decay or the equalization of things. But constantly adding energy to these systems and maintaining those systems is just
for sure. Wild. It really is incredible, like the role biology plays. But it's also, a thing to consider is entropy. How basically stating that everything will essentially come to an end, like fall apart, break up, whatever it is. Like everything, every piece of everything. It's just a matter of how much time does it take to do that. Right. And so now going back to time, it's like on a grander scale, things take tens of thousands, hundreds of millions of years to happen.
Mm-hmm.
Whereas like we'll experience an entire lifetime within our 80, 90 years, whatever, however long we live, and then you talk about, smaller objects and how fast things happen within milliseconds of each other. So the role time plays in terms of like proportion of like different matter and different things in the universe is like really, really something, interesting to look at and consider also for physics.
Yeah, I mean, also, again, just coming back to that idea of proportion, over time. I mean, music, again, being this idea that certain wavelengths unfold and they vibrate. There's vibrating, resonating bodies that create, rarefactions in the air, right? And we perceive that as a frequency, as an oscillation. And it's interesting, again, going back to this idea that certain ones are pleasant, certain ones are dissonant. Right. And it's interesting, maybe if there's like, in terms of the human faculty, like, are we picking up on something that is, destructive in nature or constructive in nature? And like, why are they pleasant to us? You know what I mean? Why did these things naturally, like chords and things like that, why do they have that quality? Because again, I mean, I feel like there can be cultural interpretations of music. Sometimes dissonant music is really pleasant. I mean, going into like metal or
it can
like
be
whatever,
used tastefully.
Yeah.
It's still not necessarily pleasant to the ear, but if you have something pleasant and then at a point throw in some dissonance, you're kind of creating some tension in there, so to speak.
Yeah, it's interesting too, because those vibrations, again, like where and how and why do we interpret them the way that we do? I mean, really, really interesting and really, really big questions. So, I mean, definitely, if you guys are listening, hit the comments. Let us know what you think about these sorts of things. You want to weigh in on this conversation, like, comment, and subscribe, all that good stuff if you want to be on the next endeavor that we're doing. So that about wraps it up for this episode. So thank you for being on The Conscious Endeavor.
Thanks for having me.
My friend Zach, and we'll see you guys next time. Take care.